Alright, so in the first video we had just finished coming up with the Y value when we plugged 13 years in, and we got $6.67 million per year. So let's see if that fits in with the pattern of the model. So if I go back over to here and I put in 13, where 13 is about right in here, and 6.67, does that seem to fit fairly well? Yeah, it does. It's in between. It's bigger than the 11 and smaller than the value for 16 years after 1980, so it looks okay. We also want to now predict the value for 2005. So that prediction, so 2005, x is 25. So we are going to put natural log of y equals 0.13 plus 0.136 times x, which is 25. Whenever you're asked to make predictions, you're simply asked to put values in for x. You're asked to put x values in. That's what it means when it says find a prediction. Put a value in for x. So I'm going to calculate this one. So I'm going to take 0.13 plus 0.136 times 25. And I'm going to get 3.53 is equal to the natural log of y, not just y. Basically, all you have to do to solve this to get y is take that and make it the power on e. So e to the 3.53. That's how you get rid of the natural log. Basically, you apply e on both sides. And e is a number. And so these things, a number that has a power, so these both sides become the exponent of e. These cancel because they're inverses, like adding and subtracting are inverses. So you get y equals whatever this is. So second e to the 3.53 power says that that person in 2005 is going to make $34.1 million per year. So let's see if that fits in with the model. So 25 is after this, so 25 says we're going to make 34.1 million. Now it does seem to be in keeping with the pattern, the exponential pattern that we notice, that it's rising slowly and then it's going up very quickly. Major League Baseball, I believe, is where the highest paid professional athletes are. So this it is possible. Maybe someone did make 34 million in 2005. The bad thing is what this is doing. Remember, this is called extrapolation. Extrapolation means going beyond what we have, beyond the data that we have. This might be okay. We're not too far beyond. All right, so let's see. We've got a little note here at the bottom. It says this method only works when the y values are positive, because you can't find the log or natural log of a negative number, and they need to start close to 0. So if you need to shift the y values, remember to shift back when making the prediction. So that's what we were doing when we were applying e to both sides. When we plugged the 25 in here, we weren't just getting y, we were getting the natural log of y, then we had to apply e. That's what that little statement means. All right, so now we've got some data on our solar system, and we, if you would have entered this into your calculator and gone through the process, it's the same process as we went through a few moments ago, or on the last video. So all of the stuff that we need is already done, it's already here, so we don't need to enter it in your calculator. If you'd like to try it and see if you get these same things, that's probably good practice. Just pause this video and give it a try. So we've got some data about our solar system. So here are the planets, and our key data is the distance in miles in the million miles from the sun. So this is Mercury is 36 million miles from the sun. Now again, please do not try to change these values back into millions or write them as millions. There's a reason they wrote them like this, so they're shorter, easier for you to deal with. Okay? And the length of the year on Mercury is in Earth years. So in other words, the amount of time it takes for Mercury to go all the way around the sun is only about 1/4 of our Earth years. So these are, we're just looking at how far away they are from the sun and the length of their year. So we do a linear regression with just entering this in list 1 and this in list 2, and we get this nice little scatter plot, okay? And there's our linear regression. Y hat equals a plus bx, or the b sub 0 plus b sub 1. There's b0 and b1. And this is our residual plot. So, does the linear model seem appropriate? No. Why not? Since the residual plot has a curved pattern. And really this, when you get the worksheet you'll have for your assignment here, the worksheet you have for your assignment is just asking you to do these exact things, and you need to sketch the things here, write the regression equation, and answer the questions. It's very simple. Okay, you do need to provide on paper what these graphs look like in the regression. So no, since the residual plot has a curved pattern. Okay, so now we're going to transform the data by taking the natural log of the y values, okay? Just the natural log of the y values. So you would have gone and done that in the heading of list 3. You would have said, okay, I'm going to take the natural log of list 2. And then you're going to do a scatter plot like we did before, and you're going to graph list 1 and list 3. Well, here is the data now. This is what the data looks like now since I changed the y values. And there is the new least squares regression line. You have to recalculate a least squares regression line every time. So you have to redo stat calc 8, and this time it would have been with list 1 and list 3. So now my equation is the natural log of the y's, because I took the natural log of the y's, equals 0.2784 plus 0.0017. Okay, do the residual plot, and now the residual plot has a curved pattern the other way. So again, does the exponential model seem appropriate? Same thing here. No. Same reason. It has a curved pattern. No. Not appropriate. So that wasn't the best way to go. Well, what can we do now if that method doesn't work? Well, we've already taken the natural log of the y's. Now we go in and we can take the natural log of the x's. So we can go in and take the natural log of the x's. So you'll go in now and you might just want to redo in list 3, do in the heading of list 3, do the natural log of list 1, and then go into the heading of list 4 and do the natural log of list 2. So you've got two new lists. This would be your natural log of your x's and your natural log of your y's. And again, you're doing this in the heading of the lists. These are called power models when you do this. Okay, power models. Now our equation, we're not only going to have the natural log of the y's, but we're going to have the natural log of the x's that we plug in too. So we now have a new scatter plot with a new linear regression model. You still have to do stat calc 8, this time with list 2 and list 3, or sorry, with list 3 and list 4 if you did it the way I recommended here. And so now your equation is the natural log of y equals negative 6.8046 plus 1.5007 natural log of x. And the residual plot here is pretty nice and scattered. So does this model seem appropriate? Yes, this model seems appropriate. Yes, since residual plot has no pattern. So I would say that yes, this is appropriate now since the residual plot has no pattern. So I found the best model. So now we would like to do a little prediction. It says, in 2002, researchers discovered another object orbiting the sun 4 billion miles away. Okay, so we need to change 4 billion into million. So 4 billion equals 4,000 million. So this would be our x value, 4,000 million. About how long should it take to orbit the sun? Okay, in Earth years. So this is farther away than Pluto. So we're going to use this model right here. And what we're going to do is we're going to have the natural log of y equals negative 6.8046 8046 plus 1.5007 times the natural log of my x value, which is 4,000 million. So now I'm just going to plug this in. I'm going to have to put 4,000 in, and whoops, I have to take the natural log of it, so I better just clear this. I'm going to have to, I can just type this in the way I see it. Negative 6.8046 plus 1.5007 times the natural log of 4,000. Hit enter. And so I have that the natural log of y equals 5.64228. So the only difference was, I just typed this side in exactly the way I see it. Negative 6.8 plus 1.5007 times the natural log of 4,000. Now I do the same thing I did last time, and I basically apply e on both sides, so I get y equals whatever e to the 5.64228 power is. So second e and 5.64228, and that gives me 282.1 Earth years. So it will take it 282.1 Earth years to go around the sun one time. So the farther away you are, the longer your year is. All right, almost done. We've got a little conclusion here. So there are many more transformations we can try when logarithms don't work. Sometimes taking a square root will help straighten out data. Sometimes squaring a data set or using the reciprocals of a data set will work. Besides transforming data to make it linear, you can also use many types of mathematical functions in an attempt to best fit the data. Some of these can be found in the Stat Calc menu on the TI-83, and many others can be found on computer software. So if you go to Stat Calc, you've got quadratic regression, cubic regression, quartic regression would be to the fourth power. There's natural log regression, there's exponential regression, power regression, logistic, sine, cosine, sine regression, make it like a sine curve, and then manual fit. So there's lots of options, but the only one you need to know about is the exponential and the logarithmic transformations, exponential models, power models. And by taking the natural log of the y and then the natural log of both. So the final decision about which model to use should be based on the residual plots. The model whose residual plot has the most random scatter does the best job of capturing the true form or the signal of the relationship. So for your homework, you should have picked up a worksheet that you need to do. It should look like this. So I suppose what you could do if you don't have it is you can just pause the video here and you can answer the questions based on looking at this. Just show your work on a separate sheet of paper. So you should not try to fit the answers in these little spots. You should do your work on a separate sheet of paper. So that's it. Last day of notes.